Welcome to the deep dive. We take the information you're curious about, sift through it, and pull out the key stuff you need without, drowning you in details.
Exactly. Straight to the core ideas.
So today we're tackling the really interesting world of simple machines. This is for the learner who sent us a chapter and wants a clear, full picture of these basic tools.
It's a great topic.
Yeah,
Fundamental stuff.
absolutely. I mean, have you ever stopped to think why using, say, a wrench makes loosening a bolt so much easier than just using your hands?
Or how a couple of ropes and wheels can lift something super heavy.
Yeah, that's what we're getting into today, the science behind these everyday tools based on this chapter.
It's amazing how these ancient inventions are still, everywhere. Foundational to so much technology.
Okay, let's dive in. The chapter kicks off with those common experiences, right? Like popping a stubborn lid with a spoon as a lever.
Or using a crowbar to move something heavy you couldn't budge otherwise.
Exactly. That's simple machines making work easier. And the chapter points out four main ways they do this.
And what's neat is that these different tools, the spoon, the crowbar, even like bike gears, they all work on just a few basic ideas. The first big one is multiplying force.
Right. Getting that strength boost, like using a car jack, put in some effort.
Yeah, not that much effort, really.
And this massive car lifts up. It's amazing. The chapter mentions crowbars, spades, digging soil, pulleys. It's that aha moment where the machine does the hard part.
It really is. And think about ancient constructions like the pyramids. Moving those huge stones, impossible without things like levers and ramps, force multipliers.
Good point. Okay, so the second way machines help is by changing where you apply the force, making it more convenient.
Like riding a bike. Your feet go round and round.
Right.
But that effort moves the back wheel and pushes you forward. The bike redirects your effort. You're not, pushing the ground directly.
It makes the task easier for you. Okay, third function, changing the direction of the effort.
Yeah, this is super handy sometimes. The classic example is lifting a bucket from a well with a fixed pulley instead of leaning over and pulling up, which is awkward.
And probably bad for your back.
Definitely. You just pull down on the rope, the pulley flips the direction, and often you can use your own body weight to help. Much easier.
Makes sense. And the fourth way, gaining speed. This one feels a bit less intuitive sometimes.
Maybe. Think about scissors cutting cloth. Your fingers move the handles, maybe, an inch or two? But the tips of the blades slice through, like several inches of fabric, much faster. Your small movement creates a larger, faster movement at the business end.
Okay, yeah, I see that. Like with a knife cutting, too.
Right. A gain in speed.
So force multiplying, changing application point, changing direction, gaining speed. 4 ways. The chapter then sums it up. A machine either overcomes a big resistance with less force, or it helps you gain speed.
But, and this is really key, you can't get both at once from the same machine.
Ah, the trade-off.
Exactly. It's either a force multiplier, which usually means your effort moves further, or it's a speed multiplier, which usually means you need more effort. You trade one advantage for the other. It's fundamental.
No free lunch, basically. Okay, to really dig into how they work, we need some terms. The chapter defines load first.
Yeah, load, symbol L, it's just the resistance the machine is up against. The thing you're trying to lift or cut or move.
Yeah.
The obstacle.
Got it. And effort.
Effort, symbol E. That's the force you put into the machine, your input.
Simple enough. Now, mechanical advantage, MA. This sounds important for the force multiplying part.
Oh, absolutely central. Mechanical advantage, MA, is simply the ratio of the load to the effort. So MA equals L divided by E.
L over E.
Right. It's a number that tells you how much the machine boosts your force. If MA is bigger than 1, you've got a force multiplier. You're lifting more than you're pushing, basically.
Okay.
If MA is less than 1, you need more effort than the load itself, but you're probably getting speed or maybe a bigger range of motion out of it.
And if it's exactly 1?
Then MA equals 1, like with that fixed pulley we talked about. You're not really multiplying force. You're mainly just changing its direction. And it's just a ratio. So, importantly, no units for MA.
Right, just a number telling you the force boost. Okay, next term, velocity ratio, VR. Sounds related, but different.
It is related. Velocity ratio, VR, compares the distance your effort moves, let's call it DE, to the distance the load moves, DL.
Oh.
Or you can think of it as the ratio of their speeds.
So distance or speed, not force.
Exactly. If you pull a rope, say 2 meters, that's DE. To lift a box, just 1 meter, that's DL. The VR is 2 divided by 1, which is 2.
Okay.
A high VR usually goes with force multiplication. If a small effort movement makes the load move a long way quickly, The VR is less than 1, and you're likely getting speed. Like MA, it's just a ratio, no units.
Okay, MA for force difference, VR for distance or speed difference.
Okay.
Clearer now. Then there's work input, we.
Work input, that's the work you do on the machine. Remember physics class. Work is force times distance.
Right, force x distance.
So work input is your effort force, E, times the distance your effort moves, DE. We times DE. It's the energy you're putting in.
And work output, whoa, must be the flip side.
Exactly. Work output, whoa, is the work the machine does on the load. So that's the load force, L, times the distance the load moves, DL. Whoa, will L times DL. It's useful work done.
Okay. And finally, efficiency. Symbol eta. Looks like an N.
Yeah, the Greek letter eta.
Yeah.
If efficiency is the reality check, it's the ratio of the work output to the work input. A, whoa, divided by we.
So how much useful work you get out for the energy you put in?
Precisely. Often shown as a percentage.
Mm-hmm.
And in the real world, E is always less than 1 or less than 100%. Some energy always gets lost. And again, it's a ratio, whoa over we, so no units.
Right. And the chapter stresses something important about friction and the machine's own weight.
Yes, this is interesting. Friction and the weight of the machine's moving parts, they don't change the velocity ratio, the VR. That's set by the geometry, how it's built. But friction and weight do reduce the actual mechanical advantage, the MA you really get. And they definitely lower the efficiency.
Because some of your effort goes into fighting friction or lifting the machine itself.
Exactly. Not just moving the load you care about. So a machine might look great on paper with a high VR, but friction can really eat into the MA you experience.
Got it. Okay, now the principle of a machine, it's about energy flow.
Fundamentally, yes.
Yeah.
You put energy in with your effort. The machine transfers that energy to do work on the load. The place you push or pull is the effort point.
And where the machine acts on the load is the load point.
Right. And the big underlying rule is conservation of energy.
You can't get more energy out than you put in.
Never. Work output can never be greater than work input. That breaks physics, which is why no real machine can hit 100% efficiency.
The chapter distinguishes between an ideal machine and an actual one here.
Yeah. An ideal machine is purely theoretical. No friction, no weight in its parts, no energy loss at all. Whoa equals we. Efficiency is 100%. Doesn't exist in reality.
Actual machines are what we actually use.
Right. They always have losses. Friction between moving parts is usually the biggest culprit. Things rubbing together. Ropes might stretch. Parts have weight. That lost energy often turns into heat.
So if a machine is, say, 80% efficient, what does that mean practically?
It means if you put in 100 joules of energy, only 80 joules actually go into doing the useful work on the load. The other 20 joules are wasted, mostly warming up the machine parts due to friction.
Okay, that makes the efficiency number really tangible. Now, connecting efficiency, MA, and VR, there's a formula.
Yes, and it ties it all together quite nicely. We know we.
Output over input.
And WEMO, LXDL, and we equals EXDE. So substitute those in. EXDL, EXDE. Now let's rearrange that slightly. EXDLDE. See that?
LE is MA.
Exactly. And DLDE. Well, VR is DEDL. So DLDE is 1 over VR.
So LE, MA, VR.
You got it. Or you can write it as MA, VR times E.
Wow. So the actual force boost you get, MA, is the theoretical boost VR multiplied by how efficient the machine is?
Precisely. It shows that for that perfect, ideal machine where A equals 1, MA equals VR.
But for any real machine, A is less than 1.
So MA will always be less than VR. The real-world advantage is always less than the theoretical potential because of those energy losses.
Okay, that framework is solid. Now the chapter dives into specific types, starting with levers. Simple but powerful.
And they really are. A lever is just a rigid bar, could be straight, could be bent, that pivots around a fixed point. We call that point the fulcrum, F.
And the key bits are the effort arm and the load arm.
Right. The effort arm is the distance from the fulcrum to where you apply the effort. The load arm is the distance from the fulcrum to where the load acts on the lever. We usually assume, just to start, that the lever bar itself is weightless and there's no friction at the fulcrum.
Makes sense for understanding the basics. And their operation is based on the principle of the lever, or moments.
Exactly. The law of moments. For the lever to be balanced, the turning effect of the load around the fulcrum has to equal the turning effect of the effort, mathematically. Load times load arm equals effort times.
Effort.
L times load arm equal E
times effort.
Yep. And if you rearrange that, you get L over E equals effort arm over load arm, and LE is just.
Mechanical advantage. MA equal effort arm, load arm.
Bingo. The MA of a lever depends entirely on the ratio of those arm lengths.
So if the effort arm is longer than the load arm,
MA is greater than 1, force multiplier. You apply less force to move a bigger load.
if they're equal.
MA is 1, usually just changing direction.
And if the effort arm is shorter.
MA is less than 1. You need more effort, but you probably get speed or more movement at the load end, like trying to push a heavy door open right next to the hinge. Very short effort arm, very hard.
Definitely felt that. Okay, the chapter then groups levers into 3 classes based on where the fulcrum F, effort E, and load L are. Class I first.
Class I. Fulcrum is between the effort and the load. F is in the middle, E and L are on either side. Think of a seesaw.
Okay.
The pivot is F, one kid is L, the other pushing is E. What's unique about Class I is that the MA can be greater than 1, equal to 1, or less than 1. It all depends on where the fulcrum sits between E and L.
Examples help, like heavy shears for metal, long handles, effort arm, short blades, load arm.
Perfect example.
Yeah.
Big MA1 for cutting tough stuff. But then maybe regular scissors might have longer blades relative to handles for speed, so MA could be 1.
And a simple balance scale, fulcrum right in the middle.
Equal arms, MA1, just for comparing weights accurately.
Yeah.
The chapter also mentions a long oar for rowing that's used for speed games, surprisingly Class I.
How does that work?
The oarlock on the boat is the fulcrum, F. The rower pulls between the fulcrum and their hands, E, and the water resistance is further out on the blade, L. Oh, wait, actually, let me rephrase that. For a long oar, F is the oarlock, E is the rower's hands, L is the water resistance further out. If the rower's hands are further from the oarlock than the main blade section in the water. Let me check the chapter's description again. Okay. For the long handle or used for speed, it can function like a Class I lever where the rower applies effort between the fulcrum oarlock and the load, water resistance, but the effect they focus on is the speed gain at the tip. The classification can sometimes depend on how you analyze the primary goal. Let's stick to the clearer examples, perhaps. Crowbar, definitely Class I. MA1, pliers, Class 1.
Okay, let's move to Class 2 then. How are they set up?
Class 2, load is between the fulcrum and the effort. L is in the middle, F is at one end, E is applied at the other end.
Like a nutcracker.
Exactly. Hinge is F, nut is L in the middle, you squeeze the handles at the end, that's E. The key thing here, the effort arm, distance from F to E, is always longer than the load arm, distance from F to L.
Which means?
MA is always greater than 1. Class 2 levers are always force multipliers. Okay.
Bottle opener fulcrum is the cap edge. Load is lifting the cap. Effort is pulling the handle. Wheelbarrow wheel is F. Load is in the barrow, L. Effort is lifting handles, E. Always MA1.
Yep. Very effective at lifting or applying strong force.
Makes sense. And finally, Class 3.
Class 3. Effort is between the fulcrum and the load. E is in the middle, F is at one end, L is at the other.
Like sugar tongs.
Perfect. Hinge is F, you squeeze in the middle, E to pick up the sugar cube at the end.
Yeah.
What's the defining feature here?
The effort arm, F to E, looks shorter than the load arm, F to L.
Always. Which means the MA is always less than 1.
So you need more effort force than the load force? Why use them?
Speed, or range of motion. The load end moves further and faster than where you apply the effort. Think fire tongs, tweezers.
Or lifting something with your forearm. Elbow is F. Bicep pulls near the elbow, E. Hand holds the load, L.
Exactly. Your bicep works harder than the weight you hold, but your hand can move quickly over a wide range. Fishing rod is another classic, Class 3. Allows a quick flick to cast the line far.
Fascinating how these 3 classes cover so many tools. And connecting them to the human body, that's really cool.
Isn't it? Our own bodies use these principles. Nodding your head, that's Class 1.
Spine is the fulcrum. Weight of head is load. Neck muscles provide effort.
You got it.
And Class 2, in the body.
Standing on tiptoes. Your toes on the ground are the fulcrum, F. Your body weight acts down through your ankle foot. Your calf muscle pulls up on your heel, E, FLE configuration.
Wow, okay. In Class 3, we mentioned the forearm lifting.
Yeah, elbow, F, bicep attachment, E, load in hand, L. FEL shows how fundamental these are built right into us.
Incredible. Okay, moving on from levers, the chapter gets into pulleys.
Right, pulleys. Grooved wheels on axles used with ropes, for lifting mainly. Can be single or combined into blocks and tackles.
Starts with the single fixed pulley. We sort of touched on this.
Yeah, the axle's fixed, doesn't move. Ideally, effort equals load. MA equals 1.
And distance pulled equals distance lifted.
Yep, VR equals 1. Ideal efficiency, 100%.
So no force advantage. Its main job is
Changing direction.
Yeah.
Making it easier to pull down rather than lift up, like hoisting a flag. Convenience.
Got it. Now, the single movable pulley. This one sounds more promising for force help.
It is. Here, the load hangs from the pulley's axle, and the pulley itself moves up with the load. Rope is fixed at one end, you pull the other end.
And the advantage?
Ideally, the MA is 2. The load is supported by 2 rope segments effectively, so you only need half the force.
Right.
E equals L2.
Nice. Double the lifting power, sort of. What's the trade-off?
Distance. You have to pull the rope twice as far as the load moves up. DE equals 2 times DL, so VR2.
MA2, VR2. Makes sense. Ideal efficiency still, 100%.
Ideally, yes. But the weight of the pulley itself adds to the load you feel, and friction reduces the real MA. And you often have to pull upwards, which isn't ideal.
So you might combine it with a fixed pulley just to pull downwards again.
Very common. Use the movable one for the force advantage, add a fixed one to redirect the effort conveniently.
The chapter's comparison table for fixed versus movable is pretty handy here. Okay, but what if you need even more mechanical advantage for really heavy stuff?
Then you combine pulleys. Use systems. The chapter outlines 2 main ways. First, one fixed pulley and several movable ones, each on its own rope.
Okay, how does that work out for MA?
If you have n movable pulleys in this setup, the ideal MA equals 2 to the power of n. So 2 movable pulleys gives MA4, 3 gives MA8. It grows fast.
Wow. And VR.
Also 2 to the power of n. Ideal efficiency, 100%. But lots of separate ropes can get messy.
Yeah, I can imagine. What's the more common system?
The block and tackle. You see these on cranes, ships. It uses 2 blocks of pulleys. One block is fixed up high, the other block holds the load and moves. And crucially, there's one continuous rope threaded through all the pulleys.
Ah, one rope. Simpler to manage. How's the MA calculated here?
It's simpler, too. Ideal MA is just equal to n, the total number of pulleys in both blocks combined. Or, equivalently, the number of rope strands supporting the movable block.
So if there are 4 pulleys total, MA is 4.
Ideally, yes.
Yeah.
And the VR is also n, so MAN, VRN. Ideal efficiency, 100%. Your effort gets multiplied by the number of supporting rope segments.
But again, reality check. The weight of the pulleys matters, especially the moving ones.
Big time. The chapter introduces WE for the weight of that lower movable block with its pulleys. This W acts against you.
How does it affect the MA formula?
The actual MA becomes roughly N minus W divided by E, where E is your effort. So the heavier that bottom block W is, the more it reduces your actual MA.
But the VR stays N.
VR still N, based on the geometry.
Yeah.
But the efficiency drops too.
Yeah.
E becomes about 1 minus W divided by N times E.
So lightweight pulleys are really important for good efficiency in a block and tackle.
Absolutely critical. Lightweight materials, low friction bearings.
Yeah.
That's how you get closer to the ideal end on times force multiplication.
Yeah.
Minimize that W and minimize friction.
Okay, that covers a lot of ground. From the basic definitions, MA, VR, efficiency, through the 3 classes of levers, and into single and combined pulley systems, it really paints a clear picture of how these simple machines work.
It's quite elegant, isn't it? How these few principles, leverage, redirection of force, trading distance for force, explain so many useful devices.
Totally. And you start seeing them everywhere once you know what to look for.
And understanding this foundation helps make sense of much more complex machines, too. They often just combine these simple principles in clever ways.
Right. So for you, the learner, we really hope this walkthrough hit the mark, giving you that clear, solid understanding without getting bogged down.
Yeah, hopefully those aha moments clicked, connecting the concepts to real-world tools and even your own body.
We saw how machines multiply force or speed, how levers work based on where the fulcrum sits, and how pulleys give us different ways to lift things more easily.
From the nutcracker to the fishing rod to the block and tackle on a crane.
So here's something to chew on as you go about your day. Now that you're tuned into simple machines, just notice how many you use or see. But also, think bigger. How has developing these fundamental tools actually shaped, well, everything? Human civilization.
And looking forward, where might innovation in these seemingly simple areas still lead? What's the next ingenious lever or pulley system waiting to be figured out?
Definitely food for thought. Keep an eye out for those everyday examples.